Hello all, welcome to this course on Elements of Mechanical Engineering. This is a course offered to Aeronautical and Civil Engineering students in 6th semester. Currently we are in the first module where we are studying energy sources and different thermodynamic laws. So far in the previous lectures we have seen what are the different methods that are used for calculating the first law of thermodynamics problem. So apart from that, we have seen different systems, surroundings, environment. So depending on this, we have generated 4 laws which are related to thermodynamics. They are 0th, 1st, 2nd and 3rd law. So in this lecture, we are going to see the problems on 2nd law of thermodynamics. So my name is Atchuta Ramacharyulu and I am working as an assistant professor in the Department of Mechanical Engineering. So the first example for today is, first we will see the question. A reversible heat engine receives 3000 kilojoules of heat from a constant temperature source at 650 Kelvin. If the surroundings is at 295 Kelvins, determine the availability of heat energy and unavailable heat. So in this question, there is some given data and we have to calculate 2 parts, that is availability of heat energy, how much heat energy is available. And the second one is unavailable heat, how much heat is not unavailable. So these 2 are the things we have to calculate in this problem. Now let us write what is the given data in this question. So in the question, the given data is the reversible heat engine receives a heat of 3000 kilojoules. So this is the heat given in the question, 3000 kilojoules. And the constant temperature is also given, 650 Kelvin. And also the surrounding temperature is also given, 295 kelvins. So everything is given in kelvins, the temperature. And whatever the temperature, the heat is there, that is given in 3000 kilojoules. So that is what we written here. Q1 is equal to 3000 kilojoules. T1, which is the temperature of the system, is 650 kelvins. And T naught, that is the temperature of the surroundings, that is 295 Kelvin. Now we have to calculate these 2 things, available heat energy and unavailable heat energy. So let us solve this problem. First of all, we will calculate the change in entropy. So when we are supplying some heat to a system, according to the 2nd law of thermodynamics, the entropy will increase. So according to the 2nd law of thermodynamics, we have to calculate the change in entropy. So here this is the formula for change in entropy, which is dQ by temperature, change in enthalpy divided by change in heat divided by T. T is the temperature difference. Now from the given data, we can simply calculate here, this is for a multiple systems. So here integral sign is used for if there are more than one system. In this condition, we have only one single system. So that is why we are directly writing the formula as Q1 divided by T1 plus T naught. So T1 is nothing but the temperature of the system and T naught is the temperature of the surroundings. Now T1 plus T naught will give you the temperature that is which the system is undergoing. So T1 is equal to 650. T naught is equal to 295 and Q1 is equal to 3000 kilojoules. Now using this, we have calculated the change in entropy as, so this is delta S, this value is 3.17 kilojoules per Kelvin. See here, the units are also very simple. We have the units for Q as kilojoules and units for temperature as nothing but Kelvin. So we got the change in entropy as 3.17 kilojoules per Kelvin. Now, so this is what we have calculated is, this is change in entropy. We have not calculated how much amount of heat is available. So we have to calculate that. So the availability of heat energy will be calculated by using this formula. So Q1 is nothing but the amount of heat supplied to the system during this process minus T naught. T naught is the temperature of the surroundings. T naught is the temperature of the surrounding and it is multiplied with delta S. Delta S is nothing but change in entropy. Just now we have calculated. 3.17 is the change of entropy. So by using this, we can simply calculate Q1 is nothing but 3000 minus T naught. The temperature of the surroundings is 295 multiplied by 3.17, that is change in entropy. So finally, we will get the answer as 2064.85 kilojoules. So this is the answer. So this is the amount of heat available in the system. Okay. So by using this equation, we have calculated the available heat in the system. Now we will calculate the second part. So this is the first part we have done with this, and now we are going to calculate second part. So the unavailable heat. So unavailable heat is nothing but the value. It can be calculated by using the change in entropy multiplied by the temperature of the surrounding. Simply we will get this by multiplying these two, T naught into delta S. So T naught is 295 multiplied by 3.17. This is change in entropy, and the value will be 935.17 kilojoules. So this is the value of the unavailable heat which is not present in the system because it is converted into another form. Okay. Now, so in this question there are 2 points asked to be calculated. So the first thing is the available heat energy. So that is we are denoting this available heat energy with the capital A. So its value is 2064.85 kilojoules, and the unavailable heat which is represented with UA, and its value is 935 kilojoules. So from this, what we can observe? So in the question, it is given that this is the value of the heat that is given to the system. See here. Here a reversible heat engine receives 300 kilojoules from a constant temperature source. So this 3000 kilojoules is the heat supplied to the system. Now, while the system is undergoing some kind of changes, what happens? There are 2 kinds of energies. First one is available energy and second one is unavailable energy. Now, this available energy is nothing but the energy that is consumed in the body and it is available to be used. So, this is 2064, approximately 2065. This is available energy, and unavailable heat energy that is present in the body is 935, approximately 935 kilojoules. If we sum these two, we will get 3000 kilojoules, which is exactly the number equal to the heat supplied to the system. So whatever the heat that is supplied to the system, according to the second law of thermodynamics, according to the first law of thermodynamics, the law of conservation of energy, the energy be neither created nor destroyed, but it is converted from one form to another. So here we can clearly understand the first law of thermodynamics using this question. So here the amount of energy or heat supplied to the heat engine, it is converted into 2 different forms. One is available and second one is unavailable heat. But they are converted from one form to another form, but another energy is not lost or gained. Okay, it is converted into another form. Simple. Now, this is the first question. This is done. And now, we'll see the second example. So, in this second example, let us see the question first. Air in a closed vessel of fixed volume, 0.15 cubic meters, exerts pressure of 12 bars at 250 degrees centigrade. So, first of all, we were given a closed vessel with air, and it has a volume of 0.15 cubic meters and it exerts a pressure of 12 bars. And the temperature of this closed vessel is 250 degrees centigrade. Now, from here, if the vessel is cooled so that the pressure falls to 3.5 bars. So what happens is, initially the temperature of the vessel is 250 degrees centigrade. Now when I try to cool this system, what happens? It will convert or it will reduce the pressure to a value of 3.5 bars. Initially the pressure is 12 bars. When I cooled the system, it reduced it to 3.5 bars. Now, what we have to calculate by using this condition is determine the final pressure, heat transfer and change of entropy. So there are 3 points we have to calculate here. That is final pressure, heat transfer and change in entropy. So these 3 points we have to calculate. First of all, we will write what is the given data from the question. So V1 is the value, that is volume of the contents in the vessel. So we have air, the closed container have air here. So the volume of air initially is equal to 0.15 cubic meters and pressure is 12 bars. Now we are converting this pressure into kilonewton per meter square. Okay, simply we'll multiply that with 100. Okay, 12 into 100 will gives you the pressure in kilonewton per meter square. Why we are converting this? Because mostly we will use System International for calculating all the formulas and problems. So that is why I have converted the pressure from bars to kilonewton per meter square. Okay, now I got the pressure value. This is initial pressure. Initial pressure is equal to 1200 kilonewton per meter square. And again, P2. P2 is nothing but the final pressure. This is also converted into 3.5 multiplied by 1000 will gives you the pressure in kilonewton meter square. So that is in System International. And the temperature, initial temperature is given in the question. T1 is equal to 250 degrees centigrade, where I will convert this 250 plus 273 will gives the value in kelvins, 523 kelvins. So this is the given data. Now we'll see how to calculate this these topics. There are 3 topics asked for to be calculated. Now first of all, I will take the ideal gas condition equation for getting the molecular value. Okay. Now from this is ideal gas equation, where mass is equal to P1 V1 divided by R into T1. Here M is the molecular weight of the gas which is present in the closed vessel. M is the molecular weight. P is the pressure of the air initially, and V1 is the volume initially, and T1 is the temperature initially. And now R is the universal gas constant. It is a constant value. It has the value of 0.287. Some units are there. Now we are going to calculate this molecular weight. Here, see here, in the previous slide we have calculated the values of pressure, volume and temperature. Here P1 is equal to 1200, T1 is equal to 523 and V1 is equal to 0.15. Now I will write those here. P1 is equal to 1200, P1 is equal to 1200, V1 is equal to 0.15. And so the units are kilonewton per meter square. Here volume is in meter cube, and temperature T1 is equal to 523 Kelvin. So whenever we are writing the formulas or values, we must denote the units. If we forget the units, we are not going to tell what are the units, what are the value is indicating. So we should always remember to give the units for any value. Okay. So while doing numericals, giving the units is very important. So here pressure value is 1200 kilonewton per meter square. Volume V1 is equal to 0.15 meter cube and T1 is equal to 523 Kelvin. Now, while I will substitute these values in the given formula. Okay. Now I have substituted P1 1200 and V1 0.15 and T1 is 523 Kelvin. Now here the value of R is 0.287, which is a universal gas constant. It is a standard value for any problem. So finally we got the mass, molecular weight of the body, molecular weight of the air present in the vessel is 1.2 kg. So this is the weight of the air present in the vessel. From the given data, we have calculated the weight of the air. Now we are going to calculate the first point. That is the first question asked is we have to calculate the final pressure. So for constant volume process, we have a equation called T2 divided by T1 is equal to P2 divided by P1. So T2 divided by T1, from which we can calculate the final pressure. So using this equation, we can calculate the final pressure. So this is a constant volume process. Okay, this equation is valid only when the process is having constant volume. Volume is constant. There is no change. There is no change in the volume. So from this equation, we can simply write T2 is equal to T1 into P2 by P1, where we will substitute the values. So the T1 value is already given in the question, that is 523, multiplied by P2 by P1, initial pressure and final pressure. So final pressure is 3.5 divided by initial pressure, that is 12. So here we have converted this into kilonewtons per meter square, even though these values are same because the numerator and denominator will be multiplied by 100. So they are cancelled. So that is why the values given in the question, which are in bars, they are directly written here, 3.5 divided by 12. And finally, we will get the temperature as 152.54 kelvins. So this is the temperature of the air present in the vessel when it is compressed to a lower volume and it has reached this temperature. Initially, the temperature is 523 Kelvin. Now the temperature is 152 Kelvin. The temperature has reduced. So this is the first question asked. So we have calculated the temperature. So that is 152.54 Kelvins. And second one is heat transfer. We have to calculate the heat transfer. So in this question, we have a closed container in which air is present. We are applying some pressure on this container so that the temperature, volume are decreasing. Now I have to calculate how much of heat is transferred to this container while doing this process. So for this I am going to calculate Q value, that is Q is equal to M into Cp multiplied by T2 minus T1. So this is a basic equation where we are going to calculate the heat supply to the system. So for calculating the heat supply to the system, we have to take into consideration the weight of the content that is present in the vessel. So the weight of the content is 3.17. Sorry, the weight is different. We have calculated in the previous slide. So the weight is 1.2 kg. Weight of the air present in the vessel is 1.2 kg multiplied by Cp. Cp is nothing but the constant pressure coefficient. So it is a constant value, that is 1.005. It is approximately 1. And T2 minus T1. T2 is the final temperature after compression. So that is just now we have calculated 152.54 minus 523. So finally from this we can get the value as we'll get a negative value because here the temperature T1 is more when compared to T2. So that is why my negative sign is represented here, minus 446.78 kilojoules. So this is the amount of heat that is transferred. Okay. I'm not telling that heat is supplied to the system. Heat may be supplied or removed. Okay. Now in this condition, heat is rejected because this negative sign indicating that the heat is being rejected from the system. So heat is removed from the system during this process. So that is why we have written here negative sign indicates that the heat is rejected from the system. Okay, heat is rejected from the system. That is why negative sign is indicating. So this is the value of heat transferred during the process. Okay, so this is the answer for second question. And third one is change of entropy. Now in this question we have to calculate the entropy change that is happening inside the system while the system is undergoing the compression process. Okay. Now change in entropy is nothing but this is delta S is equal to mass. So that is molecular weight multiplied by Cp natural logarithm T2 by T1 minus universal gas constant into natural logarithm P2 by P1. So this is the formula when we have the temperature and pressure values. Okay, when we have temperature, initial and final temperatures and pressure values, then we can use this formula. So delta S is equal to molecular weight multiplied by Cp natural logarithm T2 by T1 minus universal gas constant multiplied by natural logarithm P2 by P1. So using this equation, we can calculate. We have all the values. The molecular weight is 1.2, Cp is 1.005, natural logarithm T2 is known 152.5, and T1 is 523, and the universal gas constant is 0.287, and the initial and final pressures are known. Initial pressure is 12, final pressure is 3.5 bars. So we have substituted all the values in the given formula, and finally we have calculated the change in entropy as minus 1.06 kilojoules per Kelvin. Now, in the previous question, while calculating the heat transfer, we got a negative sign, and we have represented this negative sign indicating the rejection of heat from the system. Now, similarly, in calculating the change of entropy, we got negative sign. So, what is the meaning of this negative sign? Whether the entropy is positive or negative. What does the positive entropy indicates and what does the negative entropy indicates? So, the negative entropy indicates that the system has decreased its entropy. So, the system is reaching more stable condition. When it is positive, the entropy is increasing. When the change of entropy value is positive, the entropy is more increasing. That is, from time to time, the entropy is increasing. But now here in this condition, we got a negative sign where the entropy is decreasing. Like we are compressing the air to a lower volume where its temperature is decreasing, pressure is increasing, and volume is decreasing. Okay. So because of these conditions, there is a change of state where the entropy is decreased. And also from the second question, we know that heat is rejected from the system. So when the heat is removed from the system, the molecules will get low entropy. So this is the question. So the next question, this is third question for this lecture. First we will see what is the question. A domestic food freezer maintains a temperature of minus 15 degrees centigrade. So here the temperature is given. The ambient air is at 30 degrees centigrade. So this is the temperature of the ambient air. If the heat leaks into the freezer at continuous rate of 1.75 kilojoules per second. Okay, now from the surroundings, the hot air is entering into the freezer at a rate of 1.75 kilojoules per second. What is the least power necessary to pump the heat out of the freezer continuously? So we have to calculate what is the amount of power required to pump out this heat that is entering into the freezer when the temperatures are given. The freezer is at minus 15 degrees centigrade and the temperature of the ambient air is 30 degrees centigrade. So I have to calculate how to remove this heat that is entering into the refrigerator, and I have to calculate the power necessary for this action. Now let us see what is the given data. So here TL nothing but the temperature inside the freezer, that is minus 15 degrees centigrade, and I have converted this into Kelvin. So 273 minus 15, because the temperature is given in negative, I will subtract this where I will get 258 Kelvin. And TH, that is temperature on the ambient air. Temperature of the ambient air is 30 degrees centigrade, where I will convert this into 273 plus 30 will give 303 Kelvin. So this is the temperature of the surroundings, that is hot air present outside the refrigerator. And heat supplied is nothing but QS is equal to 1.75. So this is simply can be taken as heat supplied, that is heat that is entering into the system. Okay, because the temperature is high outside, heat will automatically enter into the cold place. Now we have to calculate the power. For power, we have to calculate work done. Work done per second will give you the power. Okay. Now, we'll see how to calculate this one. So, first of all, we need the quotient of performance, COP. So, this is the general formula that is given for any refrigeration system where we have to calculate the COP. COP is nothing but coefficient of performance. Every refrigeration system will have this coefficient of performance. Based on this COP value, we can estimate or we can design the refrigeration in a better way. So it will indicate the efficiency of the system. Okay. Now we are going to use the COP from Carnot cycle. So Carnot COP is equal to T lower temperature divided by T higher temperature minus TL. Okay. Now all these values we have. So 258 divided by 303 minus 258. So for this we get the value 5.73. So this is the quotient of performance from Carnot cycle. So this is theoretical value where we will get this from the formula. Now actual COP has to be calculated. That means how much amount of heat is supplied or taken out of the system and how much of work is done during the process. So by using these three parameters, COP, QS, that is heat supplied or rejected, and work done. So these three values are used to calculate the amount of COP, that is. So we will calculate by using this formula. Now here COP is equal to QS divided by work done. So in this, COP is already known. Just now we have calculated the Carnot COP. This is theoretical value. Now we will substitute this 5.733 as COP. QS is given in the question, that is 1.75 kilojoules per second. So what are the units for COP? There are no units. Here you can see COP is the temperature, Kelvin divided by Kelvin. So there are no units for COP. It is a ratio. And divided by work done. So from this we can get W is equal to 1.75 divided by 5.733. So from this we can get the value of work done as 0.305 kilojoules per second. Carefully observe the units. So here the units for 1.75 is nothing but kilojoules per second, that is given in the question. Now after calculating this, 1.75 is in kilojoules per second. There are no units for 5.73. So that is why the final work that is done by the heat pump is given by 0.305, which is in kilojoules, not in kilowatts. Kilojoules per second is actually equal to kilowatts only. Okay. So this is the value, that is the least power necessary for the refrigeration system to pump out the heat. So this is the amount of heat required. Okay. So W is equal to 0.305 is the amount of heat required to pump out the heat from the refrigerator so that it will remain at minus 15 degrees centigrade. Okay. So this is the third problem. So where we have calculated the least power required, that is 0.305 Kelvin. So in this problem we have used the new formula called Carnot cycle, Carnot COP. COP stands for quotient of performance, and from that we have calculated the heat that is supplied to the refrigerator and work done or power required to reject the heat. So far we have seen three questions in this lecture. So first one is based on, this is based on a reversible heat engine. So this is simple problem where we have calculated change in entropy. And in the second question, we have calculated the final pressure, temperature and heat transfer and change of entropy. This is also same. And in the third question also, we have calculated the amount of power required to reject the heat from the system. That is all for today. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.